Another draft physics video presentation. So, been doing some research, and I did find the electron experiment in 1960, one-ish, German, and even cites in the translation how this paper never got, any kind of notice. It's not in the textbooks, um, you know, and it's just kind of funny that they'll use electron diffraction. Experiments where it's really electrons reflecting off of a grating rather than going through actual slits. Well, anyway, so I haven't gone through all of it piece by piece to figure out, but basically they're doing the experiment in an electron microscope, and they have to highly magnify the effects, like thousands of times, kind of. To make it possible to see, because the irony sort of is that it's really hard to manufacture an actual slit that's really small, and so the smallest slit they could practically manufacture is actually the size of the slit that they say is you're using in the double slit experiment, where you can just scratch a piece of glass. Well, to actually make a physical surface that you cut that thin is really hard to do, that can withstand getting bombarded by electrons. But even that, the whole thing has got all kinds of little bugs in it. Like they're using a thin foil and cutting slits that are actually 500 nanometers. They're actually the wavelength of visible light. They're supposed to be the wavelength of an X-ray, but anyway, don't even get into all that. So I mean, if you were to take the experiment and turn it into a light experiment, you'd have like preposterous circumstances where you have like a 5 centimeter slit, instead of a half a millimeter, it'd be 5 centimeters, and the distance would be 4 miles to the target, and 4 miles from the source, and all kinds of crazy numbers. And obviously, if you were to do that, if you would have huge distances like that between the surfaces, it means there's a ton of wavelengths, like a million. So the truth is like a million wavelengths for the electron in that slit, maybe more. And so the bars would be tiny because there's actually a million of them in every 90 degrees. And so that's why you have to magnify. But then you'd say, well, why don't they spread further? You only get 7 or 8 bars out of the experiment. Lots of things don't make any sense. So anyway, I haven't gone through like I said, all of that to explain all of that. What I really want to do is just to explain how I think X-rays are being created, and how the mechanism that allows electrons to be the creator of different electromagnetic radiation, and it really just has to do with their speed. And so is there anything else I want to say? So yes, I just want to concede there, yes, the experiment was done, and there's other versions of it, that happened in the 70s, so I want to look those up. So they did do 2 slit electron experiments. It's just that they're not as simple as just shining electrons and looking at the image. It's technically, there's a whole bunch of other instruments in the experiment doing all kinds of things that one can be suspect about. Now, in this experiment is also kind of bizarre that they're using a film thin enough that they can cut it to make semi-straight slits, and yet still 70% of the electrons are going right through it. And they are claiming it doesn't matter. It seems to me that would matter, but anyway, seems to me that might be why they're creating X-rays, and that they're taking an image of X-rays. But anyway, we'll get to that in a future argument. It's hard to tell the difference between an electron and an X-ray in terms of detecting. Often the detectors that'll detect fast-moving electrons are often the same materials that'll detect X-rays. So it's not a very, you have to be a little careful. What do I want to do? I want to turn the camera on. And yeah, that's all I want to do, turn it on. There. That's what I did. All right, now we'll move that over here. That should work. All right. So, I've got lots of room to write. Principle. So the idea of moving electrons is that you create an electrical potential difference. That is, you have a lot of electrons on one side, very crowded electrons, and then very few, relatively speaking, on the other side. So you have this differential. And the idea would be is you could sort of understand that now this is an electric field. Now, I'm arguing it's always the same field. It's magnetism, it's charge, it's whatever you want to call it. But the idea is that there's a force that reflects off electrons, so we're just going to deal with that, so we don't need two colors. If I was to do colors, what you'd see is more red stuff is coming off of one side and more blue stuff is flying off the other side, but it's really not the feature that's important. The feature that's important is you understand that when electrons are stacked together like this, and say if I had an electron in there, he's perfectly comfortable. But if I throw one here, he's going to end up reflecting the force that's moving in this direction. Okay? The electron reflective force is obviously going to go this way because it's all going to reflect from this side, and it's not going to reflect from this side. It's going to get absorbed by this side. This side's going to absorb a lot of force. This side's going to reflect all the force. So you're going to understand that any force that's in there is going to be going this way. Okay, a lot more of it's going one way than it's going the other way because there's more electrons over here. But the idea would be as an electron pops out here, then any force between these electrons is doing this pressure magnification thing where you could understand that if there was this idea of a ping pong paddle and the ball could just keep bouncing back and forth between the ping pong paddles, you can understand that's a constant pressure and completely dependent on proximity, and that there would be the reflections would be happening at the speed of light, so there's a real incentive to get further away from each other, and there are constant pushes this way and a constant push this way because of that reflection. And that's really what's happening to the electron. So when you heat this element, this metal surface that you have charge on, so you've charged it, now you're going to heat it, okay? And when you heat, you can heat it first and then charge it. It really doesn't matter which order you do it in. But the point is once you heat it, that's when you're popping these electrons off. Okay, you're ionizing the surface and electrons are getting popped into the field. So if you just understand that the field is pushing more force in one direction than is coming back in the opposite direction. And so any force then is going to build up, there's going to be a huge amount of force building up here, a huge incentive for this electron to start getting out of here. This electron can't go anywhere, the one on the surface. It's got a whole bunch of other crap behind it, so it can't do the moving. So this electron has to do the moving. And that's what's propelling the electron. And so it's getting propelled, okay, by a real mechanism. Essentially, I would argue that what happens is that the electron is essentially collecting the momentum. So as energy reflects off one side and hits it, so the electron now goes 10% of the speed of light because it has a bit of force stuck on it. And then if it gets hit again, going in this direction, then that piece of force sticks on it and it goes 20% of the speed of light, and so on. So it ends up having a chain of energy stuck to it. So you can sort of understand that a bit of extra, this more force, this river of force going this direction, okay, and you can sort of understand that that river starts to build up because it's only going 10%. The first one hits, it's only going 10% of the speed of light away, so obviously these things going the speed of light can catch up to it really easy. But as you get the electron going faster and faster, right, as you build up this little chain, obviously the stuff behind doesn't catch up, and now all the conversation is going to be about the stuff coming forward, because as stuff hits it forward, then it reflects one of those pieces, and then it loses a little bit of the velocity. So that's the basic idea, is it builds up a whole bunch of this potential to go this way, and that's the X-ray being created right there. So that's the high frequency, right? Or the gamma ray or whatever, that's being created. And the catch is there any way to move this electron in such a way, or change the electron in such a way as that you release all of that into the atmosphere as a single event. Okay, so I'll probably get rid of this. And alright, so another part of how they create X-rays, alright, is they take an electron gun, a cathode ray tube. So cathode rays are really just electrons. And so you have your heated element, you're sending electrons at a velocity, depending on the voltage. And to make X-rays, all they really do is just let the cathode ray, the electrons, hit the glass of the vacuum chamber, and then all of a sudden a bunch of X-rays fly out. Where the electrons hit the glass, the bunch of X-rays fly out. So that's the simple way they originally made X-rays, was just to allow the electrons to collide with something, then their momentum, the stuff pushing them, so the argument would be they have a bunch of stuff pushing them, and now there's going to be a bunch of collisions. So let's say they hit another electron. What's going to happen? Well, the force between these two electrons is going to build up as they get closer and closer together. This force is essentially going to be converted into this force. You can sort of understand that as this plows in, it keeps having it. So even though, okay, this one's sending bits going this way, well, and then this one loses a bit going that way, but it's still pushing this way. So it uses up another bit going this way, so to speak, and that causes a reflection that way, and this causes this to reflect. But anyway, so this force ends up moving into this position, and essentially could just push this electron. But the trick is the two of now this electron isn't got a whole bunch of other electrons behind it, right? It's just a single electron. So the point is, as it starts making that conversion, the force here starts to balance with the force here, and now this electron might end up going that way, and this electron might will go that way, but I mean at some other speed. So anyway, I'm just pointing out that all you're really doing is pushing force into different containers, different size containers. And as you change the size of the container, you change the frequency, the difference between the distance of the bits of force. So the chain of force you've collected ends up spreading, or becoming further apart, depending on how much distance there is between the electrons that are interacting. So how much speed this has, how much stuff it's collected, all depends on what you're going to get as a result. And the speed is going to be essentially correlated to how much energy it has pushing it, because to lose speed it had to lose some of these bits, and only the electrons that still have a lot of bits are still going to be capable of producing, say, an X-ray, because they have to be able to push in with enough force to cause this transfer of the energy. Now if this electron goes this way and the force goes that way, that's sort of the idea of releasing the frequency. So maybe I'll take a pause and try to explain that another way to make it clearer. I think I'm recording, yes. Okay, so this is kind of draft, by the way. That's the point of it. So you take something like lightning, right? So you have a bolt of lightning, and the idea is everybody's kind of noticed this, that you pick it up on your radio. So every time there's really a spark, that goes from one place to another, one of these spark things, the spark is actually creating all kinds of electromagnetic radiation. So it's creating low frequency radio, it's creating microwaves, it's creating X-rays, gamma. So it's creating the entire spectrum is flying off of that lightning bolt. So when you hear it on the radio, that's just telling you, okay, and you see the light it makes, you're seeing, okay, it's creating everything in the spectrum. all forms of energy at a frequency. Okay, so it's making all kinds of it. So it's making stuff that's coming out with a big distance between it, consistent distance, and stuff that has a small distance between it. So it's creating all the frequencies that are possible. And so what's the real function? Is that you're creating a whole bunch of these ions, all right, where you're knocking electrons off of the atom. All right, so a bunch of electrons are getting knocked out of their atom, and so you're essentially creating a voltage potential. You're creating a plus side and a minus side. So you're doing the same thing essentially as just charging it with the charged plates and creating an environment for those electrons to move through. Now the trick is, it's not happening in a vacuum. It's a conductor, and the environment around it is conductive. And the key is as the electrons move into the environment, they collide with each other. And they collide with each other, based on the energy between them, based on what's trapped between them, what can be trapped between them. And they'll tell how much pressure there is and which way they deflect. So, in this kind of circumstance, this one doesn't have much choice but to push this one this way and this one this way. So they're pushing in all kinds of different directions, and the truth is, if they push fast enough, that is, they move the electron quickly into the field, the electron's going to reflect, more force just from its movement. So as I pointed out before, if I could move this piece of chalk really fast towards you, it would collect all the energy between in that distance, that 1 foot of distance, and it would take all of the photons that are heading for the piece of chalk that would have hit it eventually, and it's sending them back to you all at once. So if I move it at the speed of light, that's what it'll do. It'll take all the energy and send it all in one. It'll all be lined up in one big blob. So it'll take stuff that was spread out. The stuff was here, 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 and it'll convert that into this. So all this stuff that was in this whole area of a foot will end up being in this area of a millimeter. All right, theoretically. So there'll be a whole bunch of stuff in a whole bunch of distance, a whole big box, and it's going to be put into one tiny location. Now obviously if you go something less than the speed of light, you can understand that it's just going to take this stuff and cut that box in half. So it's going to take the stuff that was in the box, that has a certain separation naturally. All right, so you have this area of space, and the separation is, this. And you're basically, when I move something quickly, what I'm going to do is take that space, cut it in half. All right, now the things are still in it, but now their distance between each other has been cut in half. So you've taken something that had a big frequency and you've made it into something with a very small frequency. So going something less than the speed of light towards you means that I'll send the light to you by magnifying whatever frequency the stuff already had, whatever distance the stuff had coming in. So if I'm hitting a bunch of red light, let's say there was a bunch of red light coming towards me, and I move this quickly, I'm going to be converting it into blue, into ultraviolet, because I'm going to hit it much quicker than its natural reflection time. I'm going to decrease the time interval between when it would reflect off this object. So it's not going to reflect in the normal sequence, it's going to be simply shifted, right? So it's going to be blue shifted moving towards and red shifted moving away. So that's what electrons are doing. So when an electron moves quickly from one location to another location, it's shifting whatever energy was coming at it. And whatever energy was coming the other way, it's shifting exactly the opposite. You could sort of theoretically understand that any light that was coming towards it from the direction that it's going, the electron's moving in, is obviously now going to have more time before the reflections happen. So it's creating an opposite, red shift for every place it's making a blue shift. It's making a red shift somewhere else. But that's essentially what's causing, all of the different forms of radiation. There's a bunch of electrons moving a bunch of different speeds into the field. So some of them get hit directly. So the electron that is part of the experiment, that you shot very quickly into the material, like the glass wall, you shot electrons into it very quickly. Some of the electrons move just a little bit because you barely hit you barely interrupted their field. It's like something being far enough away from the Earth gravitationally. Some moon could be far enough away where it could just fly by the Earth and barely interrupt us, barely disturb us, barely cause any attraction between the two things. Obviously this is repulsion, not attraction, but I mean it's the same concept. It's being controlled by a field. And so the electrons don't really hit each other, they actually bounce off of each other's repulsive force. And so some bounce off fast, some bounce off slow. This one bounces off slow going this way, this one bounces off fast going this way. So it all depends on what speed they go at, depends on what kind of conversion they're causing.
Stop doing that.
All right, so anyway, so the point is I'm just, I have been over some of this before, but I'm just trying to tie it all together, this idea, this simple idea that if you understand the universe is full of energy coming from all directions, you can understand that if something is reflecting that energy and I move it in that field, it's going to change what the field is producing. So it is the speed of an electron that makes the different varieties of radiation, and specifically the X-ray. And that really what you have to do is have two electrons collide, where they collide substantially, like completely into each other. Okay, and that way you're going to transfer, you're going to cause an acceleration in the other electron, and that acceleration is going to have stages to it. So when I bang an electron into an electron, this electron has to communicate with its force with the other electron. So this one can't just jump to the speed of light. It has to be pushed to the speed of light also. So there's a time that it takes it to gain this acceleration, and while it's doing that, that's when it's creating the X-ray. And because as it starts to move quicker and quicker, it takes a field that was full of all kinds of crap, might have been in random places, and it's going to end up absorbing it and making it into a new frequency. So as it accelerates into the field, it blue shifts everything that's coming at it in terms of the reflection. And by doing that, it also will end up creating some sort of resonance frequency, some sort of it'll take some of the, obviously the bigger the space something's in, the more random the differences. The more possibility for distance, the more possibility for erraticness in the distances. But the smaller I make the space, the smaller the distances become, and the smaller any differences in the distances become. Yeah. All right. And so, so there's specific things about X-rays, and it's not just like regular light. It's not that easy to create X-rays that all have the same frequency. So the whole point would be is that the X-rays are coming out kind of mixed, of having a variety of frequencies. So the same argument would hold that X-rays are going to be just as likely as regular photons to have a piece go this way and a piece go that way and a piece go that way, and then those pieces would be combined in order to create something that's a visible X-ray that media will respond to. But that's where we get into the detector problem, where if you're using some kind of phosphorescent material to detect things, the material is going to react. If I hit it with the whole electron, it's going to light up, and it's also going to light up if I hit it with just the energy, just the X-ray. So that's the part where it gets a little more complicated. So I have to do more research on that. All right, let's see if there's anything else. See if there's some other way to explain it. Yeah, see if we can find a third way. All right, maybe I just try to keep it simple. So just keep it simple with this understanding, this analogy. I move the chalk quickly, it collects all the energy that's in that space that would have hit it, and it compresses it. So it takes stuff that has a big frequency and it turns it into stuff with a little frequency. So that's how the basic fundamental way that an X-ray is created is just by speed of an electron. The faster I can move an electron, the more I can compress the energy and take a regular red photon, and turn it into an X-ray photon. So X-rays are made by converting regular light, regular heat, any kind of electromagnetic radiation, anything in that spectrum, and merely moving into it quickly enough to blue shift it to the X-ray range. So it's just about how fast I move an electron in a direction, and that for that compression you have the opposite reaction, that in the other direction it will be doing exactly the opposite. It will be changing high frequency light, white light, into infrared. So that's the basic mechanism. Is the X-ray is really being caused by all the electromagnetic radiation, frankly, is being caused by electrons moving. And by moving, they take whatever's in the field and they magnify its frequency or stretch its frequency. And they do it in stages of movement, which means they end up having a consistent period, because they move one part at a certain speed, and then they move another part at a certain speed, and they move another part at a certain. They jerk into the field, which means they capture everything here, send it, capture everything here, send it, capture everything here, send it, capture everything here, send it. So that's what's giving it a consistent frequency from what could be just random radiation. Yeah. Okay, try one more time. Alright, I guess I'll try to do a little bit of the charge stuff just to make it understood. Colors. And the difference between the forces. So the idea of charging a surface is just this idea that there'd be a natural number of electrons to protons, a natural relationship. And so if I put an electron when it's in its natural condition here, there's just as much attraction to the proton as there is repulsion to the electron. So the electron doesn't do much, just can sit on the surface, and that would be what you'd call a free electron. It's not bound to the atoms. It's not one of these electrons that's stuck tight to an atom. It'll just be some kind of loafing electron that's just hanging around. Anyway, but if I charge this surface, you can understand what I'm doing is I'm adding electrons. I'm making these electrons closer together. So now if there's an electron here, a free electron, there's going to be a lot of more push away pressure than there is attraction to the proton. And what I'd argue is that essentially it's just a field, and that what's really happening is that you have all these vectors where energy's getting in. Alright, and all of these vectors can reflect back. So they're all reflecting. And so once the electron is outside of these bound electrons that are now piling up, well, they're not bound, they're free, but they're connected. Any electron that gets outside, inside they're safe, outside they're not safe. They're going to sense all of that extra pressure, and that extra pressure is just going to keep hitting them more times this way, more hits this way, and it'll get hits this way. And the opposite side is essentially sending more of this stuff, okay, But this stuff is irrelevant to an electron. An electron couldn't care less. It's just going to deflect that stuff. So there'll be more red coming from the positive. I mean, the more red coming from the negative. It's so backwards. And more, of the blue, the reflecting force, coming from the negative end, more blue. Coming from the positive end, more red. So the red doesn't mean anything to the electrons, so we can just plow through that. And really what just matters is that there's less blue coming this way, more blue going this way. And so the electron will start gaining speed just because it's getting hit by more stuff in that direction, reflecting, than it is stuff coming towards it that has any meaning. But there is drag, so as it moves into this stuff, it does increase it, but the drag is much less than the diminishment of the amount of force. The differential in the amount of things hitting it is much higher than the amount of extra force that's going to hit from drag, because there's much less of this stuff coming at it, so it can't make as much drag. And so it just moves, it starts to accelerate in the away direction. Yeah. Alright, so that's probably enough of a video. I will, make a more perfect, yeah, more perfect, a less imperfect, that's a better way to put it, video in the future, just to get to this point that electrons are what is changing the energy potential of the energy in the field. By moving into the field quickly, it not only changes the energy reflecting off it from one side, it changes it in both directions. It's changing the reflections. In one direction, the reflections are going to happen more quickly, increasing the frequency, and in the opposite direction, the reflections are going to happen less frequency, reducing the energy of the field reflecting off of it in that direction. And that the key is that it's not perfectly conservational, because the drag is never automatic. It's when it shows up is randomized, and you can't do for the thing that shows up too early, you'll never see the thing that shows up too late. So it's only one half of the equation is in the, I don't want to get into this randomness argument, but you can never go to something can happen later, but nothing can happen earlier. I can't run into something that was supposed to happen yesterday, so I can never pick up the negative part. I can have the delayed interaction, but I can't have the too soon interaction, the one that happened before I got here. So I can't show up someplace and be affected by something that was too early, right? Because I wasn't here too early. If I'm supposed to be at 6 o'clock, I can't meet somebody who was showed up at 5 o'clock. I can only meet somebody who shows up an hour late. See, I can't meet somebody who showed up an hour early. I can only meet the person who shows up an hour late. So that's the asymmetry in drag. Drag has a huge asymmetry, in that the only part of drag that can affect you is stuff that's too late. The only variability drag can have is stuff that shows up too late, not stuff that showed up too early. That can't bother me. Anyway, yeah, till the next time, and such and so forth and whatnot. Yeah, that's enough. It's a I don't think it's too complex. Like I say, if you just stick with this simple scenario of something moving really fast towards you and how that would really change your world. If things really could, big things could move really, really fast. But you sort of have some of that with sound, right? If something moves really fast towards you, it creates a huge pressure wave, all kinds of stuff, all kinds of energy. And what is it really doing? It's because it's taking stuff that's happening in a whole bunch of locations, and it's making all of that stuff happen in a much shorter period of time. So everything that was in a big pile of time is happening in a much quicker pile of time. kind of like the bullet. So there's lots of analogies. So, but that's like a key concept in the universe, is this idea that anytime matter moves really fast, it's going to really change the energy profile all around it. It doesn't have to emit a photon. It's already in the environment, and all it's really going to do is change the intensity of what already exists in the environment. It's either going to make it less intense if it's going away from you, or more intense if it's coming towards you. Yeah, that's enough. Yeah, we'll call it a video.